So now we will see another data structure for this union find problem. This time the sets will be represented by a tree structure. So this is a tree representation. Again this tree will be implicit, we will implement with an array again. Now the idea is that each set is represented by a tree, and its root will have the name of the set. Second, find I will do what now? Find I will traverse up the tree, traverse a path from I up to the root to find the name of the set, because each set is represented with a tree and its root contains the name of the set. So suppose find I comes, from I we go traversing up the tree till we reach the root, and that time we find the name of the set and we return that name. That is a find I operation. And union ij links the two corresponding trees. So this union this time is very easy, because union ij, basically I will have a pointer to the root of that set represented by I, and j is basically a pointer to the root of the set representing j. So union ij will be just linking these two roots into a single. So union, now if you see with this representation, union is constant time, but the find will take time because we have to traverse up the tree, and it depends what is the depth of the tree, and we will see how to maintain this depth of the tree to be log n. So before I do this, let me take an example again. So the example is this. So suppose we have this union operations. So union 2 3. So when I say union 2 3, suppose 2 is here and 3 was here. So basically 2 will link to 3. Now in the array representation, what will happen is this. So suppose this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Suppose this is the array. So we first said union 2 with 3, and now we have made 2 to point to 3. So basically 2 will make a pointer to 3. Previously each one its name was itself. Initially 2 is a node by itself. So 2, the name of the set is 2. So now you said union 2 and 3, so 2 goes and have a link to 3. So this is a pointer to 3. So what does it mean? Basically you can maintain them as a linked list, or basically 2 will have the name 3, a copy. Now next one, suppose we have say 4 7. So 4 7, again we will have a 4 here which will contain 7. So 4 7 will basically point to 7. Now suppose the next one is 2 4. Now 2 4, from 2 we know its name is 3, and 4 we know its name is 7. So as I said, one will be linking to the other. So I have chosen that 3 will link to 7. So what does it mean? It means this, from the 3 there will be a pointer to 7 now. So this is 7. Now suppose the next one comes which is 1 2. Now 1 is a tree by itself. For 2 we go up the tree, 2 to 3, 2 to 3, 3 to 7. So this is the last. So basically 1 and 7 has to be joined now. So we make 1 to be a child of 7. So 1.27 again now. Now suppose comes 4, 10. Now 4 we can find that its root is 7. So from 4 in the data structure we go and 7, and 10 is by itself. So we will make, suppose this is 10, 7 a child of 10. So now this 7 will point to 10. So 4, 10 is done, then 9, 12. 9, 12 again you will make 9, say 12 here, a root. So 9 will point to 12. Then comes say 12, 2. Now 12 by itself, and 2 we know its root is, so while 2 will traverse 2 to 3, 3 to 7, 7 to 10. That's the root of the tree. So now this 10 and 12, 12 is the root itself. So we have to merge these two. So what we will do, this 12 is made the child of 10. So 12 will have a pointer to 10. Then say we have 8, 11. 8 is by itself, 11 is also by itself. So probably we will put 8 and 11, 8 and say 11. So 8 will go and it will be made point to 11. Now say suppose comes 8, 2. Now 8 root is 11. 2 we will traverse all the way and we will see 10 is the root. So basically we are saying 11 and 10 has to be joined. So we will make 11 to point to 10. So 11 will now point to 10. Again it's a spaghetti. 82, then say 5, 6. Now 5, 6 there are by itself, so 6 it points to 6. So 5 and 6 basically point to 6. Then the say suppose 6, 1 comes. Then 6 is the root by itself and 1 is already in 10. So we will make 6 a child of 10. So 6 comes here, so 6 is made to 10. So if I have this union operations, they will change the tree structures like this, and actually in the data structure with the array like this. So now obviously the time complexity of the find operation takes, how much time does it take? It depends on the height of this tree, because it has to traverse all the way up to the root. And union operation, suppose this find has been done, then the union operation is constant. If this find has been done, then to find the root we have to traverse up the tree, which is log n, if the tree is maintained properly, the height of the tree. Otherwise we don't know, it can be very bad. So that is the order complexity for the find operation, and once the find operation has been done, the union is constant. Now let us see how can we maintain this height of the tree to be log n, and we play the same trick now. What we do, given the two tree, you link the smaller tree to the larger one, just as before. You merge the smaller one to the larger one. So this is called weighted merging. So what does it mean? It means always link the smaller tree to the larger one. In the previous example I did not follow this rule, I just arbitrarily link between the two, but to have a log n height of the tree we have to follow this rule. So what we can do, the size of the tree can be maintained, say probably at the root, and while merging these two roots we will just check their size. So, I am going to now write the algorithm. I am assuming this, that the array has these fields. One is P, that is the index of parent, and it is itself, if it is a root then it is by itself. So, in this example 10 is the root, so this will have a pointer to itself, so designate that it is a root. So, index of parent or index to itself if root. H, or again we maintain another variable size of the tree. Initially it is, you can maintain it as 1, all the elements have size only a single 1. So, now with this I am going to write the algorithm for find operation. So, this is the function find. If Ci dot p equal to I, that means I itself is the root, equal to I, because there is a self loop we maintain for the root, then return I, else return find Ci dot p, basically give a recursive call. This algorithm will traverse up the tree. Here is the traversal. You are going from I to its parent. In a recursive call, you are doing this. So, ultimately, when you will reach the root, you will just spew out its name. That is the find operation. Now, the union operation is again the similar. So, I am going to write this union now. Union ij, if Ci dot size is less than Cj dot size, then I is less, so it will be linked to j. So, Ci dot p becomes j. Else, if this is not the case, then Cj dot p becomes I. In the other case, if both sides are equal, then you basically link one to the other, any one is fine. So, if Ci size equal to Cj dot size, then yes. So, Ci dot size equal to, you just put twice of 2 times probably Ci dot size, you just update the size field. I did not update the size field for the other one, we can update it after also, right, it does not matter. So, this is end if, or you updated it here. I did not update the size field here, that you have to update. If Ci dot p is equal to j, not only you do this, you also update the size field here. So, probably you have to write C, or it does not matter, as somebody has pointed out that we can update at the later. We can forget about this one equal to also, that entire thing we can do at the end probably. So, let me just scratch this one out. So, this is done. Then what we will do after we do this, we will just update the Ci dot, which we have made, Cj dot j size equal to Ci dot size plus Cj dot size. Update the size field, and that is the end if, and that is the procedure. Oh, actually there is something, one thing is you have to be careful. I cannot write Cj dot size because sometimes we are changing I or sometimes we are changing j. So we will do it at the point where we are changing it. So let me write it down again so that this is clumsy. So procedure, one has to be careful about the size changing. Ij if Ci dot size is less than Cj dot size, then Ci dot p is equal to j. Here you change Ci dot size, sorry, Cj dot size equal to Ci dot size plus Cj dot size, else Cj dot p equal to I, and here you change Ci dot size equal to Ci dot size plus Cj dot size, and if. Now again the claim is the height of the tree. If we do this, height of the tree is log n. So what is the proof of this? So claim, here is the claim. The height of a tree with n nodes is at most log of n. Why? Because every time you are increasing the height by 1, and every time you are increasing the height of a tree by 1, you are doubling, at least doubling the size. So how many times you can increase the height? Since you are doubling the size of the tree, only log n. So that is the logic. Similar logic as we have seen why previously it was log n. So this is the height of the tree is log n, and find operation, since it traverses the entire tree, it is log n time. And now union operation, if you include the find operation into it, then it becomes again log n. If you don't, then it becomes only order 1. Now let us see. So in a sense, suppose we have given this find, it is log n, and again the union is also log n, because most of the time you will not be given the root immediately, you will be just asked, even for Kruskal's algorithm, 2 elements and then union these 2 corresponding trees, then you have to do 2 find. So that will also have log n. So both can be now done in log n time, union and find. Now let us see, can we improve this further? And it turns out that the find operation itself, even if it does not improve the worst case complexity, but amortized complexity can further be improved. Okay, so we will not go into the very much detail of that analysis, but I will tell you the data structure and what are the modifications into this tree structure. So again, in this we will represent the sets by trees just like the previous one, but while doing a find we will do something else which is called the path compression. What is it? So this path compression is, it connects all nodes visited during a find operation directly to the root. And union remains unchanged. So we have exactly the similar data structure, all trees, they are represented by trees, but this time whenever you are going up the tree for a find operation, for each node you are visiting up the tree, you make its link to be pointing to the root of the tree. Directly point them to the root. Why? This is because the next time you do a find, it will be almost order 1. So this is the idea, and union remains as it is. So let me just take an example. Before I give the example, let me just write the function find. So function find I now looks like this. If ci dot p not equal to 0, 0 means basically it is not yet root. If it is root, if it is not a root, then ci dot p is equal to find ci dot p. It's a recursive call, and if, and return here ci dot p. So this is a recursive call, and this is what is actually doing. So initially this finds, so recursively assume that find ci dot p, it will give you the pointer to the root. Now ci dot p will be set to the root. Recursively assume it, that find ci dot p will return the pointer to the root. So ci dot p will be set to the root. So if you unravel this recursion, you will see as you go along the up the tree, this is doing what? For each node on the path, it is setting its pointer to the root. Exactly, this is doing this in this recursion. So let me take an example, which then it will be very clear. So this is the example now. So I am assuming ij now stands for this. It stands for I is equal to find I, j is equal to find j, just like Purskal's algorithm. If I not equal to j, then union ij. Okay, whenever I write I comma j, it means these three operations. Okay, so with this one, let's see. Suppose I have 2, 3. So initially it will be 3 will point to set 2. Then suppose it comes to 4. Then we have 2, then 3, then 4 will come, and 4 pointer will be on 2. Then say 1, 6. 1, 6 probably will have another one. So this is 6, which will be pointing to 1. 1, 6. So far so good. Now suppose comes, so these two together. Now suppose come 2, 6. Now for 2, 6, it will first see 2 by itself, and 6 goes by 1. 6 goes to 1. So 1 has to be joined to 2. So what we get is it has 3, it has 4. So this is 2. Then 1 will join to this. This will join to. Okay, by this operation. This will be the tree now. Now suppose comes 6, 7. Sorry, 5, 7. Suppose it comes. For the 5, 7, I will have basically 7 here, say 5 here. So these two. Now suppose suddenly comes 4, 6. Now we will see 4 and 6 belongs to the same tree. So when you do a find operation, it will find that it's 4, find 4 will give you 2, find 6 will also give you 2, and then there will be no union at all. But as a byproduct of this, what will happen, that this tree will change. How? This will look like this now. So 3, 4 remains this. Now while doing a 6, it will point, 6 will point here, 1 also points here. So all of them now point to 2. See, because while doing a 6 now, I have to traverse 6, 1, 2, and 6 is on the path, and I told you all the nodes on the path will be pointing to the root directly. That's what it is doing here. Although there is no union, only find, but as a byproduct the tree is changing. So and this one remains 5, 7. So the next suppose comes 7, 3. For 7, 3, basically 5 goes to this. So the tree looks like 2. This one does not change. 4 remains here. 6 remains here. 1 remains there. then 5 comes here, which is pointed by 7. So 7 3 will do this, because the root of 7 will be 5, 5 will be joined to the 2, who is your root of 3. Now suppose comes 7 8. Now in this 7 8, what it will do? It will go on this tree 7 5 2, and it will make 7 as a child of 2, and 8 will come and also will be made child of 2. So now the tree will look like, basically it will have everything pointed to 2, 3 4 6 1 7 5 and probably 8. So the motivation of doing this is, now everything is pointing to the root. So now more and more find operation you will try to do, they will take less and less time, because everything you are pushing towards the root. The height of the tree is becoming more towards a constant, almost, I didn't say constant exactly. It has to be analyzed what is the behavior of this operation, but it tends to decrease the height of the tree. And this procedure is called the path compression. You are as if compressing the path. Here the path was of length 2, here suddenly your path has become only 1. So a longer path becomes shorter one. So that's why it is called a path compression. And the analysis of this, I will not go over the analysis of this algorithm, but believe me that it takes this amount of time, and I will state something which probably you have not seen it yet, some mathematical term. So it will aim find operations in this path compression scheme take order m alpha m time, and this is a something which you have not seen probably. I will explain what is an m alpha m. So m find operations takes m alpha m time. So this is a amortized complexity now. So in the best case, what will happen? M operation will take order m time, but it is saying no, it is not order m anymore. M some multiplicative factor which is alpha m. I'll show you that alpha m basically is a very small quantity. For all purpose, it is almost constant. So this complexity is as good as linear, as good as order m, almost for all practical purposes. I'll show you what is this function alpha m. Okay. So and you have already seen the union operation depends on the find operation, its complexity. So again m union operation will take m alpha m. So now amortized complexity of both the ones are almost constant. It is not exactly constant because it is not m. But now you have m union and m find operations, both of them takes only order m alpha m. So amortized complexity, this is the best so far we have got for both the operations. But in the worst case, mind that in the worst case one operation can be very bad as order n. But for order m operations it will be very good. So let me tell you what is this function. This alpha m is extremely slowly growing function, is extremely slow, extremely slowly growing function with m. Almost it does not grow. Okay, it's called inverse Ackermann's function. Inverse Ackermann's function. Okay, what is an Ackermann's function? Ackermann's function is an, which is ann of n. I am just defining. I will tell you what is ann of n now. So definition is this. This is the definition of Ackermann's function, and alpha m will be the inverse of it. So the definition is ak of 1 is 2 for k is greater than equal to 1. For k greater than equal to 1, ak1 is 2. A1 of n is equal to 2n for n greater than equal to 1. These are the two base case. Now I am going to define the function recursively or with a recurrence relation. Now I am going to define ak of n is ak minus 1 ak n minus 1 for n and k both greater than equal to 2. So this is the definition, and we will see this function grows rapidly. It grows with k and n rapidly, and that's why its inverse grows very slowly. So let's see how does it grow. I'll construct a table, and immediately you'll see how fast it is growing. So here I'm putting n is equal to 1, 2, 3, 4, 5, 6, 7. It goes on. I'm not. Now here k is equal to 1. Akn will be 2, then this will be 4, 6, 8, 10, 12, 14. Basically it is 2n, that's why it is, if you go back to the definition. Then k is equal to 2, this will be 2, this will be 2 square, then this is 8, 16, 32, 64, 128. K is equal to 3, it will be 2, 2 square, it will be 2, 2, 2. This is the tower of 3 2's. This is not 2 square, this is 2 to the power 2 to the power 2. Okay, then this one will be 2 to the power 2 to the power 2 to the power 2 to the power this, right. Okay, it goes on. I am not going to fill up because this is not important for us. These diagonals are important. This, because for our case k and n are same. An is the one which is important. An is defined as ann, where k is equal to n. So diagonal elements are important. K is equal to 4. This is 2. This is again 2 square. This is 2 to the power 2. This one is again 2 to the power 2 to the power 2 to the power 2. K is equal to 4, 2, 2 square. So this, sorry, 2 square. So this one grows. Actually, this is another 2 here, and this becomes one more 2. Goes like this, and k5 becomes this. So now look at the diagonal elements. No, this is, sorry, this is right. This is 4, this is 3. So look at the diagonal elements. When k is equal to 1, this is 2 to the power 0, 2 to the power 1. K is equal to 2, it is 2 to the power 2. Only one. This is called tower of 2. Only 1 2. K is equal to 3. There are 3 tower of 3 2's. K is equal to 4. There are tower of 4 2's. So let us see, when k is equal to 4, what is happening? What is this value? This is 2 to the power 2 to the power 2 is 2 to the power 16. This is 2 to the power 16. Now what will happen for k is equal to 5? This will go to 2 to the power 256. It is not 32. 2 to the power 256, and that will tell you how it is growing. 2 to the power 16, probably you can imagine 2 to the power 256 is something, is huge, is something like 2 to the 10 to the power 25, something like this. This is something like 10 to the power 25. 10 to the power 25 is a huge number. So inverse of 10 to the power 25 will be nothing but 5. That will be your alpha m. So when m is equal to 10 to the power 25, your alpha m is only 5. So for all practical purposes, your m is never going to be 10 to the power 25, because if that is your m, no computer can accommodate your data structure, no computer can run even your algorithm. So if you just see it, k is equal to 6, 2 to the power 1024. No, this is 512. No, this is something. This is 2 to the power 256 square. So something so huge, that many molecules or that many atoms probably does not exist in this universe. Let alone your computer can accommodate something. So alpha m to be 5 or alpha m to be 6, it is not at all possible with the practical applications. But theoretically, as m tends to infinity, these also alpha m also goes to infinity. So complexity wise, you cannot avoid or you cannot say alpha m to be constant. As m goes to infinity, this alpha m also tends to infinity. So you cannot say alpha m is a constant, but for all practical purposes, it is constant. So whenever you have m alpha m in the complexity, so how do I so that is good. How do I define alpha m now? I didn't define. Alpha m is equal to minimum of n such that a of n is greater than m. And for m to be greater than say 2 to the power 256 square, alpha m is less than equal to 5 or less than equal to 6. If you are not since I have put square, put it less than 7. Actually I did not, cannot say this. So m is in the range of this, alpha m is less than equal to 6 or 7, 6 to 7 basically. Okay, just to put 6 to 7, m is in this range, alpha m will be in this range. So for all practical purpose, our order m alpha m is linear for all practical purpose. But theoretically you cannot say. However, alpha m tends to infinity as m tends to infinity. So theoretically alpha m is not a constant. So you can show basically with a refined analysis that the height of the tree is almost constant. So if you take the amortized complexity over m find operations, you will see most of the time you are moving the pointer or you are spending almost a constant time, but not in the worst case sense. Remember this is only amortized analysis, and I have not gone through the analysis because analysis is very technical here. So with this path compression technique, both union and find can be done in m alpha m time, which is the best among all the possible we have seen so far in terms of the amortized complexity. So this much we will see about the union find problem.